In this video, we discuss overlay networks, which play a critical role in many large-scale distributed systems. Overlay networks are used in various different contexts, but for the sake of concreteness, we focus on one motivating application. Assume that you want to keep data securely stored, but you have to work with unreliable hardware. Specifically, let's assume that you want to store a lot of movies on a lot of machines, say, 1 million movies on 1 million machines. Each machine has enough memory to store 1,000 movies. This is an interesting engineering problem, with many facets. Maybe this is a good time for you to consider how you would tackle such an open-ended problem. What aspects are important and how would your solution look like? Please pause the video to think about this problem for a few minutes. So how do you store 1 million movies on 1 million machines? Let's start with a simple solution and take it from there. For instance, the first 1,000 machines could each store a copy of the first 1,000 movies. The next 1,000 machines each store a copy of the next 1,000 movies, and so on. This way, every machine stores 1,000 movies, and each movie is stored by 1,000 machines. This is highly fault-tolerant, as there are enough copies of each movie. We additionally store an index table which will tell us where to find each of the movies. There are many ways to store such an index table efficiently. For instance, we can simply store a list of all IP addresses of all involved machines, and we can store a list of all the movies. This is already enough information if the kth group of 1,000 movies is indeed stored on the kth group of 1,000 IP addresses. We could also randomize the assignment by using a family of 1,000 hash functions. For each movie, each of the 1,000 hash functions would then return one of the machines, specifying where one copy of that movie needs to be stored. On top of that, we can optimize various other aspects of the problem. For instance, availability. We can geographically distribute the machines in a way that customers who may want to stream a specific movie always have at least one of these machines in close geographical proximity. This minimizes both streaming delays and costs. However, here is another major problem. What if our machines are highly unreliable? Maybe the machines are constantly under attack. Large-scale systems being under constant attack is not unheard of. One large storage provider which operates in this business once reported that at any given time, about a third of their machines are not available because they are being under attack, or updating, or for whatever other reason. It could also be that the machines are not even owned by a single company, but they are just computers that have been crowdsourced by individual participants. Large-scale peer-to-peer file-sharing systems consist of very unreliable machines. If machines constantly join and leave, who knows which machines are currently alive? Dying machines will usually not gracefully say goodbye, they will just disappear and not answer any more to messages. Who even notices when a machine disappears? If a list of all currently available machines existed, we'd have to update that list hundreds of times every second. But also, the newly joining machines are a problem. If the newly joining machines have to register themselves with a central server, that server would experience a lot of burden. Also, this central server would be an easy target for distributed denial of service attacks, since an attacker can overburden the central server by just registering thousands of fake machines every second. High fluctuation is a problem. Formally, churn is defined as the problem where many machines continuously join and leave the system. The number of total machines may stay relatively constant over time, but each machine is in the system for just a short amount of time. In large-scale peer-to-peer systems, studies have reported that on average a machine is alive for only about 1 hour. This means that every second, hundreds of machines will join and leave the system. Do you have any suggestions on how to solve the churn problem? Please pause the video and think about this for a minute. It seems that we cannot have a single machine be responsible for knowing what is going on in the system. Any machine which has to keep track of which other machines are currently alive would be overburdened. So the organizing task has to be shared among many, possibly all machines. To do this, we connect the machines in a meaningful way in a so-called overlay network. The idea is that each machine only knows a handful of other machines, maybe randomly. Let's say that each machine knows roughly 10 other machines. In an overlay network, we call these machines neighbors. This way, each machine can easily keep track of its 10 neighbors. A machine can regularly exchange messages with its neighbors. If a neighbor stops answering, it was removed from the system, or it is currently under attack. With only 10 neighbors and an average uptime of 1 hour, a neighbor machine leaving the system will only happen once every few minutes. Machines that do have less than 10 neighbors can find new neighbors by asking neighbors of neighbors. Basically, a machine looking for more neighbors can send a message into the network. The message is randomly forwarded to other neighboring machines until it finds a machine that is also looking for more neighbors. If such a machine is found, these two machines can connect by exchanging a message over the internet. Note that in a simple overlay network, two machines being neighbors is independent of their actual geographic locations. A machine newly joining the system needs 10 neighbors. As soon as the joining machine knows at least one machine in the system, it can find the others by sending find neighbor messages into the overlay network. But how does the newly joining machine find its first neighbor? Any ideas? Please pause the video and think about it for a minute. The problem of finding a first neighbor is known as the Bootstrap problem. There is no simple answer. Various systems dealing with churn have implemented various solutions. Some systems have identified a number of machines which are very stable and usually online. Bitcoin, for instance, uses the public domain name system. Newly joining machines can then query this domain name system for a list of IP addresses of well-known and stable Bitcoin machines. Alternatively, machines may also simply query the IP address of a machine they have been in contact with previously. Maybe some of these machines are online again. With that, we have all the ingredients of simple overlay networks. The machines are connected somewhat randomly, each machine only is neighbors with a few other machines, and they try to reconnect with other machines if they lose a neighbor. If a machine is looking for a specific movie, it sends a find request to its neighbors, which forward the request to their neighbors, and so on, basically flooding the whole network with this find request. If a machine has the movie in the find request, it answers the machine who initiated the query, and the movie is streamed. However, this is still somewhat inefficient. We can do better by storing the movies at some specific nodes, and instead of flooding the overlay network with find requests, we can search for movies. However, for this approach we need to understand hypercubic networks first. This completes our video. We have shown that churn, machines constantly leaving and joining, can be addressed with overlay networks. In an overlay network, each machine only knows a few other machines, and no machine knows the whole system. Thanks for watching this video.